Dr. Saurabh, maybe we can.
Yes, sir. So, good morning to all of you. And first of all, thank you for joining this webinar. So, from JNU, we are organizing this webinar, and this is the first webinar, and there will be a more webinar in the upcoming days also. And we are organizing this webinar under the umbrella of PAIR, JNU PAIR network, and we have expertise. And for today's talk, we have Dr. Dinesh Gupta ji from ICGB. And before we will start, and I would like to invite Professor Supriya Chakravarti, who is the Dean of School of Life Sciences and also the PAIR project, ANRF PAIR project project investigator. So over to you, sir.
Thank you, Dr. Saurabh. At the outset, let me welcome all of you, the speaker and also the attendees in this webinar. Same welcome step on behalf of the university in association with Anushandhan National Research Foundation, and JNU PAIR network takes this advantage of considering this consortium we have made in terms of collaboration across institutions and to initiate the series of webinars on diverse areas which are having national importance. In such, first series is on AI and healthcare, and we have an expert, Dr. Dinesh Kumar from ICGB, who has been very well contributed in this field and known as a renowned leader not only nationally but globally. We all know that AI primarily the AI-assisted image classification involves deep learning algorithms to analyze them in terms of images in X-ray or MRI, CT scans. But beyond that, AI has a multiple role, and this webinar being organized at a time when our country also organizing AI impact in different fields of science and technology and education. As you know, JNU PAIR network consisting of 6 universities, JNU being the hub. We have other spoke universities from Assam, like Tezpur University and Cotton University. We have spoke university from Odisha, Berapur University. We have spoke university from Punjab, Central University Punjab, and also we have spoke university from Delhi, Delhi Pharmaceutical Science and Research University. So welcome to all the participants of the spoke university and everyone who has joined us. And we are eagerly waiting for talk from Dr. Dinesh. So without taking much time, I welcome Dr. Dinesh to this webinar. And also we are thankful to you for agreeing in a very short span of time. It shows your encouragement and dedication to this cause of science. With this, I conclude here and welcome all of you to this webinar once again. Thank you, Dr. Saurabh, for all the initiative you've taken.
So before we invite Dr. Dinesh sir, so our program will be like that. After that, Professor Dr. Dinesh sir will give a lecture. Then after that, Professor R.K. Brojan Singh will have a 10 minutes discussion, and then question answer session will be start. If you have any question during the during the talk or after talk, you can write it in the chat box. So we will read that, or even the our expert will read that question and directly answer it from there. So formally, I welcome Dr. Dinesh Gupta sir. He is a group leader in translational bioinformatics in ICGB, International Center for Genetic Engineering and Biotechnology. That is it's near to JNU, and sir has completed his PhD from AIMS New Delhi. Sir has a vast experience regarding the bioinformatics and artificial intelligence. Sir has a key role in specifically development and application of artificial intelligence based method to address complex biological data classification problems, as well as computer aided drug designing, including molecular modeling, molecular dynamics, homotology modeling, virtual screening, chemoinformatics for the lead identification. So, sir has a vast experience regarding the bioinformatics and how the AI will be useful for the image classification and the drug development. So I'm not taking so much time. I invite with respectfully to Dr. Dinesh Gupta, sir. Sir, over to you.
Yeah. Thank you very much, Saurabh. And before I start, I would like to thank Supriyo also for inviting me and delivering this talk. Thank you, Saurabh and Supriya. And very good morning to all the participants. I'm very happy to be here. And I'm happy to learn that this is going to be the first lecture of the series. This I didn't know this earlier. So before Saurabh said we are near JNU, we are not near JNU, we are within JNU. So we are thankful to JNU for all the support, and we also run PhD program here, which is also supported by JNU. So we are always indebted to JNU, and we are within the JNU campus only. We write JNU campus in our address. So I will now share my screen. Just let me know if you are able to. You will have to permit me, Saurabh. Yeah, just a minute. I will try to. Where is my screen? Yeah, desktop one. Are you able to see my screen? Okay. Thanks. Thanks. I will just remove all these unnecessary floating controls so that we can hide video panel, hide floating meeting control. Okay. All right. So today I'll be talking about AI assisted image classification in translational healthcare, which is a topic very close to my current research interest. And I've been collaborating with several clinicians to solve various problems in healthcare. I'll be talking about a few of them to give you an overview of what kind of problems we are facing and how we are able to solve some of the problems and what more needs to be done. So I hope I will be able to cover all these topics within the stipulated time. And I think we'll have a discussion after the lecture so that we can have a healthy discussion about my presentation and the current problems that we face in this area and how newer developments are helping us in solving some of the problems. But the data availability is one of the biggest problem in this area. So I'll be touching upon that as well. So this is in a nutshell about my research areas that I am currently interested in. So basically, I'm working towards bridging computational biology and translational sciences, especially in structural bioinformatics, algorithms for translational bioinformatics. We also develop databases, and most of the databases are available on this website. And in since last 2 decades, we are also working on AI for development of classification models for complex biological data, which is now currently mainly clinical. And this is what is going to be the main topic of today's talk. So I work with histopathological slides, X-rays, scans, and ultrasound images. We also use gene expression data sets. We also use AI for solving classification problems for DNA and protein sequences from the sequencing data sets. And we also work with various clinical data sets, which are clinical metadata sets or follow-up data in order to predict what kind of outcomes a patient can expect from the initial parameters that have been investigated on patients. So this is not new that healthcare is indeed a very complex problem in India, and there is exponential growing disease burden on our already crumbling healthcare setup. So there are several chronic diseases which are making it worse. Apart from aging population, now we have increased longevity. So a sizable amount of our population is now old, which are further straining the healthcare systems globally and also in India, which demands innovative solution so that we can, with whatever resources we have, we can make it better. And there is also a dearth of experts who can properly interpret, and even if the experts who are already there, they find it very difficult to cope up with the workload that they face in various tertiary care hospitals. So, especially the images interpretation remains time consuming because each image has to be examined by experts, which takes a lot of time. And some of the times, these images can be very quite confusing. For example, one clinician may think that it belongs to a particular disease, whereas some other experts may say that it is not a disease, it's a normal. So there are lots of discrepancies apart from the fact that it takes a lot of time in evaluation of these images, and which is also subjective, depends on the expert who is going through, who is evaluating the images, and it's of course constrained by limited expert availability. And this is one of the challenge that we faced in one of the problems that we have recently solved, and which we are currently actively working on to scale it up. So AI promises to revolutionize diagnostic, treatment planning, and patient outcomes through advanced image analysis capabilities, which are not possible by human eyes. So this is one of the areas where AI is quite uh, promising, and it has already solved many problems which needs to be scaled up so that we can develop trust, and clinicians also accept it as a viable solution. They don't take it as a competition with AI. They take it as a supportive tool for their diagnosis. So there are various breakthroughs in AI which has made medical imaging classification very easy in recent years. The first and foremost is development in deep learning. For example, now we have convolutional neural networks which are available, and we also have generative adversarial network or GANs, which are dramatically enhanced detection accuracy, and it is enabling clinicians to identify diseases earlier while the disease is progressing, and with greater precision than ever before. With accuracy of these methods could be far better than any human intelligence. And also there are algorithms which allow multimodal intelligence. That means you can combine data from various modalities like images and biochemical examinations and physical examinations and so on. And all this can be fed into various algorithms which can give more accurate diagnosis as compared to clinicians who are doing it manually. And also in recent years, we can see that there is affordable computing which is now available everywhere in the world, especially in India. We have very good computational power, and government is also supporting a lot of computing facilities across India. And you must have heard about National Supercomputing Mission. And one of the NSM node is in IUAC. So I strongly would like to recommend that if you are facing problem in getting access to good computational facility, you can access the NSM node at IUAC, which is also next to JNU campus only. And it is available to all the universities free of cost. And if you require much longer period, then you have to pay something, which is also not a good amount. So all these facilities and developments in AI are going to change the way the clinicians are going to diagnose diseases, because there is a challenge of taking care of so much workload, enhancing the accuracy. And moreover, these methods can also be accessed from various remote sites. This is another advantage of using AI in diagnosis, that you can access it even from remote places where such facilities are not available. So people can just go to labs and get the examination done. And these examination reports can be fed into various AI algorithms, which may be available on the web, and they can get the diagnosis, which can be reviewed by doctors. So AI will not replace the clinicians. They can assist the clinicians in arriving at a particular diagnosis. And other in future, there will be scalable infrastructure developments. For example, cloud-based computing will allow, as I told you, that we have a node in the neighborhood called NSM, which is in the IUAC campus. So all such nodes will enable fast computing. And when you integrate AI into these compute nodes, the analysis and diagnosis and classification will be uh, very efficient. We will also have in future general medical AI, which will accept data from all kinds of modalities, as I mentioned in my last slide. So it will take data from biochemical examination, physical examination, and images, and so on, and they will be able to predict with greater efficiency. And this is, of course, going to democratize expertise. So even the most expert opinion on various kinds of clinical reports will can be made accessible to various underserved regions of India, for example. So experts will just quickly review the analysis of AI reports and give their opinion with their experience. And this is going to reduce diagnostic delays and improve outcomes in various rural areas of India. So these technological advances promise to bridge the healthcare access gap. They are going to democratize healthcare facilities in India, and it will also bring specialist level diagnostics to remote areas whilst reducing cost. So it will also reduce the cost in diagnosis, because opinion of a good expert in one stream of medicine may be very expensive, but when you involve AI followed by a review from clinicians, it will reduce the cost, and it will, of course, improve the patient outcomes, and it will be accessible to all socioeconomic groups once it is implemented. So these are the comparison between traditional approach and AI augmented future for diagnosis. A traditional approach involves manual interpretation. It is time intensive and it is limited by human capacity. Even if the most expert clinician is made to review several slides in a day, he will be fatigued very soon, and is likely to be unable to committing errors which are not acceptable in clinics. But that's bound to happen. If you are going to press too much on human capacity, it's going to make mistakes. And traditional approaches are subjected to variability, because one operator may think that it is disease, another may think it is not disease. So there will be a lot of discrepancy. But if you have additional opinion, for example, a third umpire in a cricket match, and you can easily arrive at a better solution, and with more evidence that particular diagnosis is correct or not. Whereas in AI augmented future, the analysis support will be automated. It will be real time report generation, because sometimes the clinicians are not available for giving their opinion on the fly. But if there is a delay in analysis, the patient may suffer. But if you have a opinion from AI in the meantime before the final report from clinician comes, it can help and enhance the improvement in diagnosis and proper care of patients. And of course, it can enhance accuracy, and it will be more consistent when you are using AI. And increased diagnostic throughput. You can do several diagnostics within a small span of time without any problems in delay of analysis of these reports. So today I'll be talking about AI in ophthalmology, and several algorithms have been trained throughout the globe, including India, to predict diabetic retinopathy, which is one of the very common ailment faced by patients who are having diabetes. And several methods are now indeed being now evaluated in clinical settings. For example, in AIMS New Delhi, clinicians have started using it to evaluate the efficiency of these methods. And similarly, in South India, also there are several groups, including LV Prasad and other healthcare setups, where they are evaluating diabetic retinopathy prediction algorithms for prediction of diabetic retinopathy in patients' images of their eye. So, in today's talk, I am going to talk about AI-based prediction method that we have developed for prediction of glaucoma-related anomalies in eyes of the patients who are having glaucoma in their eyes. So, glaucoma is a group of eye diseases that damage the optic nerve, potentially leading to vision loss. So here I am showing you normal eye. So it is having an anterior chamber and posterior chamber. And the posterior chamber is consisting of vitreous cavity. There is a fluid which needs to be drained into the anterior chamber. And from anterior chamber, it goes to the veins. And this is how pressure is maintained in the eye. However, if there is any obstruction in this area, for example, if there is an obstruction in this area, which is highlighted in the square, and fluid is not able to flow in a normal way, there is an increased intraocular pressure, which puts a lot of pressure on the optic nerve, which leads to irreversible optic nerve damage, which can lead to blindness, which cannot be reversed in any way because there is a damage to the nerve. So this is another close-up of the same. So this is the normal route of the aqueous humor going into the anterior chamber. And these are certain anatomical regions which help in proper flow of the vitreous humor. For example, there is a meshwork of cells which are called trabecular meshwork, which allows flow of the fluid into the veins of the eye. So this is the normal channel. However, if this is blocked, and there is another structure called Sclem's canal, which along with trabecular meshwork helps in proper flow, outflow of the fluid from the posterior chamber into anterior chamber into the veins. However, if this area is blocked, there is our anatomical changes in trabecular meshwork as well as Sclem's canal is blocked. Then the fluid accumulates, as I showed you in this slide, and the increased intraocular pressure is observed in this area. So the glaucoma is major region for blindness in worldwide. If it is not detected in time, it can lead to blindness because of damage to the optic nerve. And IOP or intraocular pressure increases due to resistance to fluid flow in the drainage system involving iridocorneal angle. So this is the iridocorneal angle. This is iris and this is cornea. So this angle is known as iridocorneal angle. So there is damage to this area. So there is a trabecular meshwork, as I told you, and there is Sclem's canal, which is also here, not marked here, but it is present in this area itself. And all this area is damaged, and which leads to accumulation of the fluid, leading to the damage to the optic nerve. So my journey in use of AI in ophthalmology started with my collaboration with a tertiary ophthalmic care at AIMS New Delhi, where I collaborated with Dr. Vinay Gupta to analyze genomic data. He had collected a lot of genomic data for various glaucoma patients, and we found out various variants and the genes which are affected in glaucoma patients. And then we also collaborated with him to predict uh, outcome of trabeculectomy, which is a treatment given to glaucoma patient in certain cases where they make a hole which acts as the alternate drainage to the fluid, which is built up in the posterior chamber. And when a hole is made in the sclera and conjunctiva, it leads to an alternate route for flow of the fluid, and it leads to decreased pressure. However, it may not work in all the cases. So, since this is a tertiary hospital, they had a 5-year follow-up study in which they had recorded meticulously all the treatment that were given to patients coming to clinic, whether drug alone was enough to take care of their IOP, intraocular pressure, increased intraocular pressure, or their trabeculectomy was successful in these cases. So we were able to come up with a machine learning algorithm which predicts whether a patient is likely to benefit from trabelectomy or drug alone can be used for providing relief to the patient. So this method was published. And then one day he showed us another set of images which were used as diagnosis for various patients, which was ASOCT images, which are anterior segment OCT images, which are done in patients to evaluate whether they have anomaly in the ICA area, iridocorneal area or not, which led us to use of AI and developing a method which we later on called predict GAD. So predict GAD is a method to predict presence of angle dysgenesis or the anomaly in the drainage area, which is very important for clinicians to know, because then they, if the anatomical damage is there in the drainage area, their treatment plan changes. So this is what we did in this development of this method. So this was again done in collaboration with AIMS Ophthalmology Hospital. So this is now available as a touchscreen device where we have deployed the various deep learning models that we have developed. And now currently we are evaluating the performance of the model in various other collaborators' labs so that we can have a larger scale evaluation of our methods. And currently this is in progress, but I will show you what we have currently developed. So it is a AI powered tool. As I showed you here, this is a hardware, and it is a smart interactive screen. So this is a touch screen in which you can upload your image and provide various inputs, which I'll talk about in later slides. And then you run the algorithm, and it gives you a prediction on the basis of three deep learning models. So no single model was able to predict with high efficiency, but the consensus of these three models is highly efficient. So this is currently the solution that we have developed, and we have already filed a Indian patent, and which is under process currently. So before I move forward, this is again to show you that this is the ICA area, and this is the cornea, and glaucoma can be divided into open angle and close angle. So you can see here that angle of the eye or the iridocorneal angle is normal in this case, whereas there is another set of angle closure glaucoma where this angle is reduced. So these are two types of glaucoma, but in our work we have used only images from open angle glaucoma, and it can be further divided into congenital glaucoma, which is primary congenital glaucoma, or juvenile onset open angle glaucoma, which is appearing in patients who are congenital, happens in patients which are from 0 to 3 years of age, juvenile from 3 years onwards to 40 years, and primary open angle glaucoma in patients above 40 years. So these three sets of images we collected, and then we trained deep learning algorithm to predict uh, occurrence of angle dysgenesis. So now I will show you the samples of ASOCT images which we have used in our deep learning model. So this is the whole image of the cross section of the eye as we get from the ASOCT scanner, and we focus on this region. As I told you that this is the drainage area. So there is a Sclems canal as well as trabecular meshwork in this area. And this is another zoom of the same area. And on the right panel, you can see that these upper two images are normal patients, which are good examples of ASOCT images belonging to normal eye. And you can see here that this is the trabecular meshwork area, this is the iris, and this is the Sclems canal here. And this is slightly obliterated here. So images are it's very difficult to identify normal and disease on the basis of these images. And these two images are belonging to abnormal eye, which are having presence of angle dysgenesis. So you can hardly make out. So for example, in this image, you can see that this can be mistaken to be a Sclems canal, and you can hardly make out. However, AI is able to detect slightly hyper reflected image area here. So this is what is not appreciated by human eyes, and there could be discrepancies in opinion of various ophthalmologists about diagnosis of these images. So this is where we used AI and evaluated our methods. So these are critical challenges if you are predicting uh, occurrence of angle dysgenesis on the basis of images. So there is lot of natural anatomical variability, as I showed you in the previous image. And features like angle dysgenesis are regulated by gene mutation that cause irregularities in ECM metrics in trabecular meshworks. So they are it's not easy to identify, and changes are subtle enough which are not appreciated by human eyes. And histopathological studies are difficult to perform. You cannot do on human eyes, and there is limited availability of glaucoma experts even in clinics or big hospitals like AIMS. There are very few glaucoma experts who are already overburdened uh, with patients. And there is poor access to diagnostics and therapeutic services, inaccessible genetic screening. You cannot perform genetic screening on everyone who is coming to clinic. And especially in resource limited settings, you cannot expect to have genetic screening. And with this problem that we set out to do this work with this objective that we'll develop deep learning models to identify angle dysgenesis or ADOA using ASOCT images. And we also correlated our deep learning model with presence of gene mutations in gold standard data set to give credibility to our deep learning model. And then we also validated AI model with expert annotations by using blind dataset prediction. We compared opinion of the experts and outcome from our AI model. And this is the study participants statistics. We included PCG patients images, which are from 3 year to up to 3 year only, and IOP was only up to 22 mmHg. It was higher than 22 mmHg. So as I told you that IOP increases, and age was less than 10 for ASOCT scan. And GOAG onset, this was the age group that we targeted, and POAG, and what were the other parameters that are here. And exclusion criteria included steroid use. So sometimes the clinicians give steroid, which reduces the intraocular pressure. So these patients we excluded. We also excluded poor image quality and other secondary conditions in the eye, for example, nystagmus or poor fixation and so on, so that we get a good quality of images for teaching our deep learning models. So when after recruiting patients, we collected their images. So there were around 800 ASOCT images. 340 images were used for model training and rest were used for evaluation. And then we used two area. One was a bigger area, which is ICA area, and second area was closing down to the TM area or the trabecular meshwork area. And then we, since the images were very less for deep learning, we performed image augmentation. So image augmentation technically produces replicates of the same images. For example, less bright images, images with contrast and so on, RGB corrections and so on. So we multiplied our images by performing image augmentation. And then we performed validation of the images that were not used for model training. So there was external validation, and we used it to compare it with controls. So this is the deep learning model training details. We trained around 19 pre-trained CNNs. So there are different models for CNN, and each model has to be evaluated. So there is no guarantee that a particular method will always work best for you. So you have to evaluate different models. And for CNN also, there's several models. So we evaluated around 19 pre-trained CNNs. So pre-trained CNNs are nothing but the models which have been previously trained on images, so that we don't have to train the deep learning from scratch. So this is particularly useful when you have a limited number of images in your training, as well as you have not so good computational power. So this can be easily done in workstations, high-end workstation with GPUs, and we evaluated around 19 models, pre-trained models, and we found that two particular models, for example, Inception ResNet V2 and MobileNet V2, were the most efficient ones. And then for each model, you have to perform hyperparameter tuning, and this can be done using various mathematical treatments. So we use SGDM, which is stochastic gradient descent with momentum. And there are several optimizers which are all available. And then we evaluated single versus combined image augmentations. So single means that no augmentations were used, and then we also compared it with the models which were trained with image augmentations. So this is a study flowchart to make it more clear that we recruited the patients, collected their ASOCT images. We cropped two areas. Bigger area is ICA, and smaller one is TM area. And then we perform 23 types of augmentations. So these are augmentations of the same images. You can see here they are slightly different and in contrast and color in some cases, and in some cases they are just rotation of the original image. And all these helped us in increasing the size of our model. And then these were used for model training. We use MATLAB to train the model, and then after evaluating, we found that these were the models which were most efficient for different parts of the cropped areas of the images. For example, I told you here that we use two different sizes of images. So for ICA area, Inception ResNet V2 was the most efficient in Model 1. In Model 2, trabecular meshwork also performed well with Inception ResNet V2. And in the third model, trabecular meshwork area with mobile network V2 was most efficient. And then after selecting the models which were efficient, we found that three different models were more efficient in combined prediction. And this was used for further validations also to prove that these three models were indeed able to predict with higher efficiency. So we used validations for external data set. We also compared the result with genotyped cohort to prove that our valid predictions are correct. And we also performed expert model comparison. So images which were not used in our training, and images which were also blind to us with the correct classification, that we compared with the experts model comparison. And then we finally deployed this model in a touch screen. And this is how we uh, deployed the final model, and this is being now being validated in our clinical collaborators. So this is, you can see here that after augmentations, this is the number of images: 8,160 ICA images, 860 TM images, and these were used. And this is a slide, again, a close-up of the areas that we use for model training. So this is a validation one, where we performed external validation, images which were not used in training. And in validation two, we compared it with expert comparisons for the images which were blind to us. And we compared the prediction results to the actual prediction from the experts. And we found that there was strong correlation. And in the validation three, we compared our results with the genotyping, and we again see strong correlation with various mutations in the genes which were found in the patients which are actually having angle dysgenesis. And these are the common genes which are found to have variation in these patients. And we indeed found strong correlation with our predictions and the genotyping of the patients. And you can see here that these are the results. Um, as I have already mentioned, these are the genes which are affected in angle dysgenesis in glaucoma, and in TM morphology, these are the genes, and in Clem's canal morphology, these two genes are affected. And we found strong correlation with our prediction with these genotyping. So more often these deep learning models are notorious for being blind boxes because they give the predictions, but they do not give you any explanation or proof why they arrived at a particular prediction. So now we have algorithms which are indeed able to provide explainability to the predictions. That is, they provide evidence that what was the basis of the prediction that they are giving as output. So we can use these explainable AI models to give additional proof to clinicians that what were the regions which were having anomaly based on which the predictions has been arrived at. So these are few sample images just to show that these are the heat maps, and these are the output from various explainable AI algorithms which show that the predictions were based on this TM area in one case. In one case, they were based on the anomalies in the ICA area, in the iris, and so on. So each model was able to predict on the basis of anomaly in a particular region. So this gives additional evidence to the clinicians who can have more faith in this AI algorithms by looking at these kind of pictures which show what were the regions in which these anomalies were observed. So this give confidence to the clinician that these explainable AI and the deep learning model are good enough for correct prediction. So, so we have to summarize. I have just shown you that the tool has a potential to assist experts in decision making on whether a laser or surgery is appropriate in intervention. So, just by looking at the presence of angle dysgenesis or absence, they can devise the treatment plan for patients. And our algorithm can pick gross as well as subtle yet significant abnormalities, which are normally not appreciable by human eyes. Our algorithms also provides explainable AI analysis to show that our classification method is based on the regions which are having angle dysgenesis, and this method has been recognized by various platforms. For example, we were selected for GPAI, which is a global partnership on artificial intelligence, where in the last year we were able to participate with various experts and evaluate our method for appropriateness to be used in clinics. And this method was also awarded the Young Scientist Award in Health Sciences to the developer of the method, which is Dr. Shweta Birla, who developed this method. She was awarded this Young Scientist Award at AIMS presentation. So this is a video just to show how our method works. So you have to select the image, and then you have to do two different kinds of cropping as shown in this image, and then you have to select two area, and after that you have to run the prediction method, and after a while you can see that there are three different predictions, and on the basis of consensus you can arrive at um, the a consensus prediction from these three algorithms, and you can then compare it with other data, and clinician can be benefited using this. And this barcode actually is there to record the outcome of the prediction so that you can come back to it later whenever required. So future plans include that we are collaborating with more and more clinical groups to further scale up our evaluations, and we are also talking to Heidelberg Engineering, who are the manufacturing company of the ASOCT machine, the images of which we have used in our method. And then we are also evaluating and developing algorithms for several other machines, because each machine will give different kinds of output and on different kinds of resolution. So these kind of deep learning methods are heavily dependent on type of machine which has been used for generating a particular image. So this is another problem while you are developing a method. So currently no method is there which can work for all the images, but it will work for images from a particular kind of machine. And Heidelberg Engineering is the biggest manufacturer of such machines. So we have used Heidelberg Engineering ASOCT machine in our work. We are also in touch with an Indian company called MedDev Plus, who have developed a portable ASOCT scanner, and they have a different resolution. So we are developing a different deep learning algorithm, which will be finally deployed in their portable scanner, which is very cheap as compared to the machines which are given by Heidelberg and other manufacturers. So if this is useful, then this machine will be very cheap and it can be easily used for screening wider populations for presence of glaucoma and angle dysgenesis. And we are also exploring new translational research initiatives which are similar to the work that I have presented here. So this work was mainly done by Shweta Birla, who is a postdoc in my lab, and this was done by with collaboration from RP Center for Ophthalmology in AIMS, New Delhi, um, by collaborating with Professor Vinay Gupta, and several senior residents and junior faculty were also helping us in getting the images and annotating them. So this is all for one work. And in second work, I have collaborated with Department of Pathology at AIMS, where we are developed a deep learning model to perform differential diagnosis of thyroid cancer nodules. So there are 7 different kinds of thyroid nodules, and it is very difficult even for most expert pathologists, and they again, even if they are expert, they have to spend a lot of time in reviewing the slide, because the whole slide image looks like this, whereas a tumor part may be here or it may be there and it may be scattered. So it takes a lot of time in evaluating each slide, and you most of the time they are uh, uh, intersecting images. Means one part of the image may be belonging to a particular thyroid cancer nodule, other one will be intermediate, which may eventually turn into another thyroid nodule, and so on. So this gives a lot of problem to pathologists because they have to scan it thoroughly, and it takes a lot of time. So this is where we collaborated with another clinical group at AIMS, um, and they gave us several images to do this work. I will just summarize this. I will not go into details for paucity of time. So there are various features based on which uh, images are classified into different thyroid nodules. Some of them can be classified on the basis of larger size of tiles. So BTID is big tiles, which can be used for identifying a particular kind of thyroid nodule. Whereas there are certain other thyroid nodule variants which can be identified on closer look at the images. So these are small tiles. And then there are certain other um, variants of thyroid nodules which can be identified only on the basis of appearance of their nucleus. And these are nuclear ROIs, or nuclear regions of interest, which have to be used in order to arrive at particular classification of thyroid nodule. So this is how normally a pathologist works. They have to do it in different stages, and this is what we uh, used to emulate in our deep learning model. So this is a 3-stage model. In first stage, we identify a particular kind of nodules, and after evaluating in the first stage, then we go on to the second stage, where we look at a bit more closer at these images, and in third stage we look at only the nucleus. And this is how we were able to come up with a method which can identify thyroid cancer nodules according to the latest WHO guidelines, and we have published this recently. In other work, we are also working on developing a deep learning model to identify thyroid nodules on the basis of ultrasound DICOM images. This is also being done in collaboration with Department of Radiology at AIMS, and we are using various models like YOLO to identify thyroid nodules and classifying them into various thyroid scores so that clinicians can review it quickly and improve their efficiency. And we are also collaborating with a group in AIMS Bhopal, where they are giving us images for facial injury, and they want us to develop a method to quickly identify the extent and type of injury a patient is coming to the trauma center. And this is still being developed. This is ongoing work. And this slide is just to highlight there are several issues like ethical and practical consideration, because even from a hospital like AIMS, it was difficult to get several images which are suitable for deep learning. So many a times you don't get images from same machine of same hues and consistency. Many images are damaged and so on. So it's very difficult to get a very good quality data from clinics. And there is also issues like transparency and accountability. You have to be critically safeguarding to avoid algorithmic biases, ensure fairness across diverse population, and protect patient privacy also throughout the AI life cycle. So many a time you must have seen that X-ray images are marked with identity of the patient. So you have to remove these regions of the image which can help in identification of the patient. So this has to be done manually most of the times. And sometimes there are data sets which are representative of only a particular kind of population. For example, if you are working with images from American population, it may look entirely different in Indian population. So then there is a need for development of indigenous image data sets for development of efficient methods which will work on our population only. So these are some of the practical issues that you may come across when you are working with images. And then there is again adoption barriers. Many a times doctors are not ready to adopt AI, and in many places computational facilities are not available. So all these are the practical issues. Even if you develop a highly efficient method, it's not so easy to convince clinicians to use it in their clinics. And the way forward is to collaborate with more and more clinicians. And this is where we have taken our one of our work, and we are now evaluating our method in larger population. So here I would like to thank you for your attention. I will be happy to take any questions now.
So, thank you so much, sir. I would like to sincerely thank you for your insightful and inspiring talk. Your expertise and practical example gave us the valuable perspectives, and we truly appreciate the time and knowledge you have shared with us today. So, before I am coming to the question answer session, I would like to invite Professor R.K. Brojan Singh for the further discussion and any comments on this
Sure.
particular topic.
Yeah. Thank you, sir.
Okay. Am I audible?
Yes, yes, Roger.
Yeah. Thank you very much, Saurabh and Professor Supriyo for organizing this kind of talk series, and Professor Dinesh Gupta. I must say that it is an excellent talk, and so we have learned a lot of things about how this AI can be used in various perspectives of the ophthalmology and the cancer and all those things and the healthcare systems, and some basic ideas of that particular AI which can be used in healthcare system. We could able to understand from your talk, and it was very critical and a very excellent talk, I must say that. And
Thank you.
just for those participants who are actually beginners in the AI use kind of things, I'm just giving for 2 3 minutes. I'm giving a glimpse of the how AI is originated and how what kind of things one can always talk about. It is just in supporting the Professor Dinesh Gupta's introduction to the AI. If you look at, we understand that we are in the era of the data science, and as you know that this particular data is multidimensional, and we are surrounded by this data, and this multidimensional and manifold data arises from various disciplines. For example, let us say physics, chemistry, biology. Then you can talk about economics and stock markets and all those things. And the complexity of this data increases in geometrical ratio, and it is huge kind of complexity, and we need to analyze this data, and AI is found to be one of the most efficient kind of technique to understand this complexity of the data and to dig out hidden spatio-temporal patterns in this complex data. And there are a few other most efficient, very efficient techniques are there. For example, let us say quantum computing, and which takes into account this neuronal machine as the quantum machine, and then they use the quantum mechanical logic gates and all those things, and to address some of the complexity of this data. And the other one is thermodynamic computing, in which these neurons are taken to be the thermodynamic machine, and they use extensive kind of algorithms based on the this kind of information theory and many other things. And these are three one most important accurate kind of data science, which data technique to analyze this complex data analysis. And one of the most important part of this particular AI is that it can able to use as a bridge between these two techniques, that is quantum computing as well as the thermodynamic computing. It can use as a bridge between these two. And if you look at the way back to the origin of this particular AI, it is long time back. It started from the 1642, in which the first mechanical calculator machine was built by French mathematician, you can say that Pascal. And then after that, 1837, the first design of the programmable machine was introduced by Charles Babbage and other Leibniz. And so from that thing, after 1 century, then the first foundation of the today's AI machine was laid in 1943, which is given by the McCullough and the Waterpitch, which says that neural network and the brain can be used as some kind of computing machine, and they can be connected bridges. And then 1950, Alan Turing was the first person who talked about that machine can able to have some kind of intelligence, and he introduced different kind of logic techniques which is the foundation of today's AI. And then there are various perspectives, and after 6 years, in 1955, the word AI was first coined by this McCarthy in 1956 in one of the Dartmouth conference, which was organized by McCarthy and this Shannon and these people. And then there are 5 landmarks in the development of the AI. That is in the 1950 that Turing test was introduced, and then AI was coined in 1956, and in 1980 then AI has been used in the industry, and in 2010 deep learning was first introduced, and then now 2020 this artificial general intelligence has been used extensively in various other perspectives. And now this particular importance of this AI has been recognized in 2024, which was given Nobel Prize to the physics as well as chemistry. In the physics, J.J. Hopfield and Godfrey Hinton was awarded in 2024, which they have laid the foundation of today's AI machine of the patent formation around in 1980s to 86. And then in chemistry, Demis Hassabel and John Jumper were awarded Nobel Prize in Chemistry for addressing 50-year-old unsolved problems of the protein structure prediction. So from this particular perspective, there are two things which one can always talk about the AI. One is that we use already developed kind of algorithms in order to address complex data sets which we have right now. And the other one is how to, you can say, develop these efficient algorithms. And in this development of the efficient algorithms, we need different perspectives from the diff mathematical tools. For example, it is the sampling of the data, sampling the reasoning. Then you have to use this very basic diff discussion on the statistics and the probability. And if you talk about the measuring errors, you have to use information theory, algebra family to in order to have some kind of storage space in the computation. And then if you talk about the efficient logics and the statements, one has to have some kind of discrete mathematics, then operation research, and many other different branches of the mathematics have to be used in order to increase the efficiency and the accuracy of the analyzing data. And so nowadays, even different branches of the mathematics, for example, let us say number theory and many other differential geometry have been used in order to address some of the complexity of these data sets also. Let us, from this perspective, one needs to understand how these data sets have to be analyzed in a very practical and useful way. And so with this small introduction, so I'm giving this to Saurabh for the questions for the Professor Dinesh Gupta. Saurabh, over to you.
Thank you, sir. So, Dr. Dinesh, sir, we have some questions from our participants. So, it is already in the chat box. If you read, or should I read?
No, I can read it, no problem.
Yes, sir.
So, first one is from Professor Ravi Tandon.
Yeah.
Hi, Ravi. Nice to learn that you are also here. Uh,
Hello, sir.
It's a great, yeah,
Pleasure.
hello.
Ganesha.
It's a great talk indeed. Thank you, Ravi. Thanks for introducing such an exciting topic. One of the issues which is mentioned that it can exclude some of the positive results, suggesting lack of sensitivity. However, what are the chances to detect false positive cases? Yeah, so this is one of the problems that we encountered, and that's the reason we had to employ three different models for consensus prediction. And consensus of the three is highly efficient, around 95%. So, and these are the practical problems since we used very few images. If you are developing a very highly efficient deep learning model, it should include more images. And whereas we are not uh, claiming that it's going to replace the clinician, it will just help clinicians to increase their efficiency. They will have some additional support for their predictions. So this is where deep learning models have limitations, that we need a lot of data in order to make them more efficient. I think this is just a proof of concept, and in coming years you will see that with availability of more and more data which is suitable for machine learning or deep learning, efficiency of these models is likely to improve. And finally, these are the models which will be very sensitive and highly efficient. They will have very little chance of any false positive or false negative.
Yeah. So,
So
sir,
this
this
is my answer.
gold standard that you take for evaluation is just like clinical evaluation. That's what is being considered, right? Because
Yes.
whenever in COVID time we were having this HRCT, so CT score out of 25, at different places it used to come different because they also have some algorithm. They used to just take the so gold standard is something that's clinician because you mentioned also that there are some cases where clinicians are not able to really pick this up because it's so in that case clinician will report it as a negative, but if it is very sensitive so it can be taken as positive. So certain issues may come up when we look for larger number of people. So, but that's indeed a really is a great thing, a great initiative. I congratulate you for doing such an excellent work. Thank you so much.
Yeah. Thank you. Thank you. And
Yes, sir. Second question.
second question is from Ingita De Munchi. Good afternoon. It was a very good talk. I had a few minor questions. Was the data set used to train the software based only on Indian population? Yes, it was only Indian population because we collaborated with AIMS New Delhi. If so, was the demographic variability considered? No, we did not have any control on demographic. Whatever data was available to us from AIMS, we used it. We did not look at the demography of the patients that were used in our training. Since demography is important, yes, you are right, it is very important. And also was the limited to binary classification or include glaucoma staging? It included only binary classification, whether angle dysgenesis was present or absent. So with more availability of more and more data based on staging, we'll may be able to come up with models which can also correctly predict glaucoma staging. Also, since it was deployed at clinical level, I had a doubt. Is it difficult to visually distinguish between normal and diseased eye in ASOCT images? Errors in clinical labeling of images could propagate into the model. Yes, you are right. The images which are used in training have to be correct. Only then you will get a highly efficient model. If the classification of the input images is not correct, it will lead to incorrect model only. So was something also done to take care of this potential error? We had to rely on our clinician collaborators. Whatever uh, classification they gave us, we used it for in our model. So it is, but we believe that they did a good job in evaluating the images before sending them over to us for training. So we had to believe on them. So next question is from Mohammad Asif. How can AI help in remote areas where eye specialists are not available? You are right. If eye specialists are not there, if they have access to labs where they can get the examinations done, get the imaging done, they can just send it to experts over internet, and they can, on the basis of AI classification, they can be efficient in giving the diagnosis very quickly. This is how it can help in remote areas. Another place where they can help is in remote areas is that we are able to come up with portable devices which can take the images. So these portable devices can be used for rapid screening of populations. For example, if there is a patient in the family who is having glaucoma, whether the other members are likely to develop it or not can be quickly checked, because the changes will occur. In IOP pressure will increase in many years, but you can identify the anatomical anomaly in time. You can rapidly screen and ask the patient to be careful. And this is how it can help in remote areas also. It's a very good question. Thank you.
Thank you, sir. So, for your insightful answer. And so, any concluding remarks from Professor Brojan, sir, so that we will